we're going to be looking at the integral, the definite integral, as the net change of a function or of a quantity. And so what we're going to do is we're going to look at a rate of change and use that rate of change to figure out how much a function changes over a period of time. All right, so the first thing I want to do is I want to look at the integral as what I would call an accumulator. You guys know what it means to accumulate, right? To build up something. So we use the integral here for, let's say, a function. If we write the integral of f of x from a to b, what does this represent? It represents the area between the function itself and the x-axis, and it gives us the area of this region right here, right? Well, how did we originally find that area? From the very beginning, what did we do to find that area? Yeah, we used approximation methods. We used a few different ones, but the easiest ones to use were the rectangles. In fact, the right endpoint rectangles. So we said, okay, let's break it up into a finite number of rectangles and find the area of each of those rectangles. And so what we're doing to approximate the integral is to use rectangles. What we would call these Riemann sum rectangles. So a Riemann sum would be a sum that approximates an integral. And then we said if we want to make that Riemann sum as accurate as possible, we're going to do what? More rectangles. So use as many rectangles as we can. In fact, if we want an actual area, we would use how many rectangles? Infinitely many, right? So we're going to break it up into as many rectangles as we can, and eventually we're going to break it up into infinitely many rectangles by using a limit. So what we're doing is we're taking all of these little bitty slices and finding the areas of these slices and adding them up. You guys remember that concept, that idea? Okay, so this is not infinitely many rectangles. I think this is 16 rectangles. Is that what you were going to say? When we have infinitely many rectangles, what we're doing is we're taking the area of each of those infinitesimally small rectangles and adding them all up. So to find the total area, we're basically accumulating all of these little bitty pieces and adding them up to get the entire area. Does that make sense? So if let's say we're driving a car and we want to know how far we drive, we could look at our speed every second or every tenth of a second or every minute or however much we want to break it up, and find our distance over that 1 second or that tenth of a second or that minute and add all those up to get our total distance. If our speed is changing, then we want smaller time intervals because, well, we want a more accurate answer. So the smaller time intervals would give us a more accurate answer. So just like this, we want smaller rectangles to give us a more accurate answer. So we're adding up or accumulating all those areas. Okay. Another quick note about the integral. Since it's an area, what are the units of an integral going to be? It's kind of a trick question. Usually when we do area, it's going to be units squared, right? But with our application problems, we're not going to have the same units along the x-axis and along the y-axis. So the area units would be whatever the units are along the x-axis times the units along the y-axis. So it might be like time, so hours times our speed, so miles per hour. So you might have different units that you're multiplying together. In fact, you're almost always going to have different units that you're multiplying together. If we think of this function here as a rate of time, or I'm sorry, rate of change, then what we're accumulating here is very small changes in the value of the function itself. So if this right here is not f of x, but f prime of x, then each of these rectangles is going to represent a small change in f. So if we find this area here, it's going to tell us how much f changes from the left edge of that interval to the right edge of that interval. And if we add up all of those small changes over an interval, then it tells us how much f changes, the function itself changes from a to b. All right, so that's one way to think about an integral, is it adds up small changes. In this case, if we're integrating a rate of change, what we're doing is we're adding up very small changes in a function to get a total change in the function, or a net change. This is another way to think about a definite integral. If you remember, the second fundamental theorem of calculus was the theorem that we use to actually evaluate an integral. So if we have a definite integral, then we take an antiderivative. Remember, big F, when we talked about the second fundamental theorem, the big F could be any antiderivative of the little f, which means that if big F is the antiderivative of little f, then little f is the derivative of big F, right? So we could take any antiderivative and evaluate it at b and a and subtract it. So big F of b minus big F of a. That's just the second fundamental theorem of calculus. I actually don't like this notation because you actually have to say that big F is an antiderivative of little f, or you would say that little f is the derivative of big F. So what I would do, what notation I like better is just make these little f's, and then make this the derivative of little f. And then what this tells me is actually something a little bit more than what the second fundamental theorem told me. It tells me that if I take the integral of a rate of change, because remember, a derivative is a rate of change, right? So if I take a definite integral of a rate of change, then that just tells me the difference in the ending value of the function and the starting value of the function. So this integral of the rate of change tells me how much the function changes over that period of time. And that is really useful. It's one of the most useful things of an integral. So if we know how fast something's changing, say how fast air is being pumped into a balloon, we can integrate how fast or that rate air is being pumped into the balloon for the amount of time that it's being pumped in and figure out how much air was added to the balloon from when we started. What we can do with this, if we want to know the value of a function at some time, let's say that I want to know the value of f at some time, we'll call it b, just because it's right there. What I can do is I can solve this equation here, and I get an equation that looks like this. I can say, okay, the value of f at b is going to be equal to the value of f at a, some starting value of f. And that starting value is important because if I don't know the starting value, then all I know is how much it changed. I don't know where I started, so I don't know where I end. All right, so I need to know some starting value. And I don't know why I did that. Let's do x. And so this formula right here is really just the second fundamental theorem of calculus solved for one of these numbers. And it says that the value of a function at any point is equal to the value of the function at some other point plus the integral from the one to the other of the rate of change of the derivative. So again, this rate of change, if we accumulate the rate of change from a to b, from one time to another, then that tells us how much it changes total. If we add it to where we started, then we figure out where we ended. All right, so this is something else that we talked about a little bit earlier. This is kind of, it's like a definition you might see in a textbook. If the derivative of f is a rate of change of f, then the integral from a to b of that derivative gives us the change in f from a to b. So if we say that this is the velocity of a car, if I want to know how far the car went from, say, t equals 1 hour to t equals 3 hours, then I could put 1 in here, put 3 in here, and integrate that velocity from 1 to 3, and it's going to tell me how far the car went during those 3 hours. Or how, actually, I shouldn't say how far it went. It would tell me its displacement. So how far it is from its starting point when t equals 1. Okay? So one last way to look at this, I wrote a formula that looks just like this with just variables in different places. If we're given a rate of change and we're given an initial condition, we can write the function itself by using this formula here. So the function f is going to equal a starting value of f plus the integral from that starting value to whatever x value we want of that rate of change. Now the only reason I use t here instead of x is because I use x as my upper limit here. If you guys remember, we talked about this a little bit with the first fundamental theorem of calculus. We don't want a variable here that's also here. It causes problems, so we don't want to do it. We can talk for many hours about why if you want, but I don't really want to. So this formula right here is really, really, really useful and would probably be useful enough to go ahead and write it down if you haven't already.